right now. I know we are a little bit early, and because today is an interesting situation. Um, the power to my house, electricity to my house, is actually down right now. I am relying on just mobile technology. Um, let's see. So in addition to not being able to use my usual 4K monitor, I'm actually just using the laptop's own internal battery, using my cell phone for network connectivity, and that's why I did not turn on my camera because um, there's no actual light, to um, that can be used to shine on my face. So it's gonna be an interesting day. So far, I think the streaming is still up and running. Yeah, Toshio, that's going to be interesting. Okay, it makes a very interesting day. And on top of that, right before this class, I have another 1 hour meeting on Zoom, also using just my cell phone. So everything seemed to work okay. I mean, so far, I do not have any problems yet. So there's that. All right. So I think I got everything set up and ready to go. The only thing that is not set up yet is my um, tablet. So let me see if I can get that set up. All right, so that's starting up. Oh, I also have my solar panel, so-called generator, which is really just a gigantic, lithium-ion battery hooked up to my laptop computer. So that's kind of my backup. It's trying to charge my laptop um, at the same time, and then my laptop is connected to my cell phone using a USB cable. So my cell phone is not going to die anytime soon because of that. All right, and now I can go to today's notes and do a screen share from there. So it looks like we can still get most of the technology working. It's just a little interesting. Uh, Not exactly. My power is out, but it's not an accidental thing. Um, Smud had to replace some of the utility poles around my neighborhood, so I knew ahead of time that they would have a power fail today, or it's gonna be that won't be with I will be without power today. So it's not unplanned; it is planned. But last time they did something like this in my own yard, they got power, resumed at about 3 o'clock, and that was on a Friday too. So it didn't really interfere with any of my activities. But today they started a little bit late. I think there's a tree in front of the utility pole, so they had to trim the tree and make sure the work environment is safe before they can get it to work. Um, yep, doesn't look like my. Oh, okay, never mind. My laptop is not going to work because it doesn't have a Wi-Fi signal to connect to. um, Earlier, I was using a Wi-Fi hotspot, through my cell phone, so my tablet was working, my computer was working. But now that I switched to USB tethering, my uh, I didn't have the setup to use the tablet, to use my laptop computer, as a gateway to get outside to the internet. I could have set it up, but I didn't really quite prepare for that today. So anyway, all right. So first thing first, are there any questions about the exam? Does anyone want me to review the exam? Because I thought it's fairly straightforward, in a certain sense, kind of less difficult compared to the practice exam. Okay, well, since there are requests, I'll go ahead and do that. All right, so let me sign in to, oops, don't save, and I got the wrong password. Okay, let's try that again. All right, so let me go to Google Drive. Relax, I'm not gonna show the answers, to of any students, test. I'm going to show my own. And as you probably expect, there are many different versions of the same kind of questions. So yours is very unlikely to be the same as mine, but I can only show one. So here we go. Okay. All right, so let's go ahead and take a look at the exam. So if my streaming starts to stutter because it's running out of bandwidth, just let me know. Um, but I think so far everything is good. All right, so reading the questions first or reading the instructions is very important because we got a few predicates defined here. The first one, P1, is basically saying that f is indeed a function using d as domain and e as the codomain. I hope people recognize this particular quantified statement. P2 is checking whether something is injective. P3 is checking whether something is surjective. And as a result, we have this definition here. F is a function, using D as a domain and E as a codomain is bijective if and only if PB, B for bijective, which is really just a conjunction between P2 and P3, and then we have injective, but not surjective, having P2 being true, P3 being false, and then we have injective, but not injective, but surjective, which is having P2 being false and P3 being true, and then we have not injective and not surjective because it has both P2 and P3 being false. And well, the operative word here is barely, okay, because you did finish it. And then over here we have the definition of the largest subset of X, that is blah blah blah. Okay, so that's the definition of what is the largest subset, and so on. All right, so now let's go on to the first question. So my first question is not going to be the same as your first question, and as a result, I am going to use this only as an illustration. So part one is to examine C being the intersection between A and B. So let's go ahead and work this out. So we need the answer of what is the intersection between A and B. So we can see that 0, 4 is in both, 0, 2 is not, 3, 0 is not, 2, 1 is not, and then we got 1, 1 in both, and then 3, 3 is also in both, and 1, 2 is not, 2, 2 is also in both, and that's it. Alright, so next question is what is the value of P1 of this particular what is the predicate here? So if you are familiar, if you already know what P1 means, it basically means it is a function where everything in the domain is mapped to one and only one thing in the codomain. All you have to do is count, right? 0, 1, 2, 3. Okay, so it is true. If the answer is false, okay, so we can ignore that. If the answer is true, characterize C as a function. And this time I specifically name the domain and the codomain. So the domain is named as 0, 1, 2, 3, and then the codomain is 0, 1, 2, 3, 4. And so now the question is it injective? And if it is injective, that means you have to map every element in the domain to a unique element in the codomain. So in this case, let's check it, right? So we're looking for unique elements as the second item in each two tuple, and we can see 1, 2, 3, 4, so they're definitely unique. So we say yes, and since the answer is yes, we don't have to say why it is not injective. Is it surjective? So let's check whether it is surjective or not. So surjective is definitely going to be false because there are 5 items in the codomain, and yet we only get 4 items in the domain. So something is not going to be mapped. So the answer is no here. And then we have to explain if it is not, why is it not surjective? Explain this specific instance of C, its domain, and its codomain. So in this case, we can say element, let's see, 0 in the codomain is not mapped to. All right, so that's it. That's part 1. And let's move on to part 2. Part 2 is looking at the union between the two sets. So now we just have to specify the union. So 0, 4, 0, 2. I mean, just list everything in A first. So I'm doing it in a stupid way now because I could have copied and pasted. So let's copy and paste here. So I understand you guys want to talk about your exam and what you think of the exam, but right now I'm explaining the answers, so that might be important at this point. Okay, so now we just have to add things that are in B but not in A to complete the union. Alright, so let's check out what is in B but not in A. 0, 1 is one of them, and let's see, are there more? 1, 1, 2, 2, and 3, 3. So that's the only one. All right. So this is actually answering what is K. So let me copy and cut and paste. In this case, oh, okay, never mind. Instead of cutting, I just typed X. So here is cut and paste. And then we want to find the largest set L, which is a subset of K such that L is a function that is not injective and not surjective. All right, so let's find out how we can get something out of the union such that L is a function that is injective but not injective and not surjective. So all right. Non-injective is easy, right? Because we just have to map 2 different things from the domain to the same thing in the codomain. So I am going to try out 2, 1 and 1, 1. We still need something from 3, and we still need something from 0. Okay. So 3 can map to 0. 3 can map to 3. 0 itself can map to 2. It can also map to 4. And it can also map to 1. Well, we got a lot of choices here, so it's entirely up to you. Let's map everybody to 1 except for 0. Actually, 3 cannot map to 1, right? 3 can only map to 0 or 3 itself, but 0 can map to 1. There we go. So if such a subset L is found, what is it? So we'll just copy and paste this particular set. Oh, okay. Okay, Control X and paste it here. What is the domain to make this work? Well, the domain you don't really have much control over, so 0, 1, 2, 3 is going to be it. And in this case, we want the codomain to have at least 0 and 1, but we also want an extra 1 so that it is not surjective, because the question is asking it cannot be surjective. So now we move on to number 3, or part 3, and this time we're looking at the difference. So things that are in A but not in B. Alright, so let's check out what is in A but not in B. But guess what? We have the answer already, because all we need to do is to take everything that is in C and remove those things from A, and that would become the difference. So I'm going to shrink the font size a little bit, or shrink the screen a little bit, just so that I can see the question and be able to answer at the same time. Alright. So now we have 04 is not it, 02 is one of the elements, 30 is one of the elements, 21 is one of the elements. Okay, so we got 21, and then we have 11 is not, 33 is not, 12 is not. 12 is one of those elements. So here's 12. And then we have 22, which is also not. So that becomes the difference. And this time we want to find the largest subset Q that is a subset of M. This is M, such that Q is a function that is not injective but surjective. So we don't want it to be injective. And let's see. It is injective as it is. So maybe I made a mistake. Huh. Okay, let me just try that one more time. 04 is in both. 02 is only in A. 30 is only in A. 21 is only in A. 11 is in both. 33 is in both. 12 is only in A. And then 22 is in both. So we got this. Oh, okay, never mind. Brain fart, total brain fart here. So as it is already the proper answer, because right now we have something that is not injective, and it is also, now surjective is easy to figure out. Alright, so right now we just have to say what is the domain to make this work? 0, 1, 2, 3. And what is the codomain to make this work? So we want it to be surjective, so we only want to list the elements that appear as the second item of the two tuples. So we got 0, 1, and 2, and that's it. So that's all for question number 1. And okay, are there any questions about this one? Okay, so I'm gonna go back to look at the text chat channel and see if there are any specific questions other than people saying that they do not have enough time. All right. I'm confused why you defined P2, P3, and I only needed you to use P1 for part 1. Yeah, but the other ones, are also needed, because when I ask you for the largest subset that is, injective and not surjective and stuff like that, that is when you need to use the other P2 and P3, because the definition of the largest subset that is blah 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 makes use of P2 and P3. Exam with different questions using different P. I'm not really sure what that means by when Wilson mentioned that. And then we have, we were asked if they are injective or surjective, but not P2 or P3. Yes, but that's because, surjective and injective are defined using P2 and P3. Copy and paste saved me on this test. Yes, I specifically told the class that you can't copy and paste from within the same document. So that's why. The next one is I really messed up by not realize P1, P2, P3 were the quantified definitions for function, injection, and surjection. Well, they are in the instructions, and I was hoping that people would read the instructions carefully. And then the next one is, okay. Oh yeah, I spent a big chunk copying each down in order to understand what they said before seeing I didn't need it for a whole lot. Those P1, P2, and P3 definitions were not new at all. We have been using those definitions for a while because when I first introduced the concept of injection and surjection, those are the quantified statements that we have used. Um, oh wow, I never thought to use C for M. I just did M manually each time. What about 1, 1? What about 1, 1? 1, 1 is only in A. It's actually in A and in B, so it would be a part of C, which is the intersection, but it would also appear in the union, which is K, but it cannot be in the difference, which is M, because it is in both, so it cannot be in the quote-unquote difference. Isn't that in A but not in B, and it should be in M? You mean the 1, 1? No, 1, 1 is in both. See, here's 1, 1, and there's 1, 1, 2. 1, 1 is in A and in B. I would like you to read the predicate part. Yes, okay, I can do that. Or translate rather. That's what we did in class a long time ago, and also in the faraway galaxy. I explained my methodology for injective, bijective, and surjective without using P2 and P3 by name. That's okay, that's fine. I understood the question, but it took me time to make sure I typed / copied correctly. Okay. So it's mechanically using the editor, using copy and paste. And by the way, I'm not even using a mouse. I'm using a what they call a um, I think it's called a track point, on an IBM keyboard. So that's why my cursor positioning is not quite as accurate as those of you who have a gaming mouse taking a test. My concern is, did we have to say because P3 equals 1, the set is da da da? And the answer is no. You can just basically answer as the way that I did here. And I'm sure I typed correctly as what I wanted. Okay. All right. So I think I got all the text messages cleared out. So that's question number 1, and the other questions are pretty much the same thing, except, okay, the only differences would be the qualification of C would not be the same for every single question. Some are injective only, some are surjective only, some are bijective, and I think some are going to be not injective and not surjective. For part 2 and part 3, basically the same thing. Um, so the question is asking for something that is not injective and not surjective. For this particular one, other times I would be asking for injective and not surjective. Other times I will be asking for injective but not injective but surjective, and some other times it will be bijective. And the same thing for part C, part 3. So those all kind of vary, all over the place. And also the given sets, A and B, are also going to be, guess what, all over the place. So that's how I generated these questions, so that no two individual of this class would share the same question. Not that anyone would try to find out whether other people end up with the same question, but the answer is no. All right. So does that kind of answer the questions, basically from 1 to 5? All right, excellent. And then we move on to questions 6 and 7, which I am not going to even say anything because these two are actually exactly the same, as the question 6 and the question 7 from the practice exam. The only difference is the way I scatter x, y, and z and the way I nest g are different. Okay, possibly some of you may even get exactly the same setup as in the practice exam, although the chances of that happening is pretty low. And then the numbers here are also potentially different, from one person to the next. And then for question number 7, same deal. Okay, same deal. The three given numbers, in K, they will be different, and then the way G is nested to get to the answer would also be different compared to the practice exam. But otherwise, it's exactly the same format. So the method that I used in the practice exam would be applicable to the actual exam in this case. Yep, you can do the spreadsheet. You can also, just kind of work this out individually, because what really is important in this case is the method. The spreadsheet helps in the sense that we got all the equations already set up, and the spreadsheet was something that I worked out in class. And if you use that spreadsheet, as long as you did not collaborate with somebody to come up with the spreadsheet during the exam, it's perfectly okay. Not a problem. Okay, excellent. The grades. It depends on how quickly I can grade these open-ended questions. I think this one is easier to grade compared to the practice exam, so I'm hoping it's not going to take me as much time. But I cannot make any promises so far, because I would say maybe a week. Okay, maybe give me a week. So next Wednesday, I can try to target next Wednesday to get everything graded. Um, because I also have the other class, which is CISP440, which Jonathan is also in. And that one has got more people, and the questions are also kind of more interesting to grade. Um, so that is that. Yes, absolutely. So in addition to making your own exam available to you for view only, I can even give you the key. Because I have the computer generated key. Um, also, well, it's not quite ready yet. I have to make a few tweaks, to make it work. But otherwise, I can actually give you both your own exam and also the key, so that way you can assess how you are doing in this particular test. All right. Oh, Jonathan, the other Jonathan is also in 310. Jonathan Camarena. I did not notice, because the other class is really big. We got like close to 60 students. Oh, okay, I see. All right. So I'm gonna I will keep this one on the tab, but otherwise I'm gonna move on to some other um, topic. So we're going to continue with the discussion of propositional logic. So let's go ahead and get to propositional logic here. So there we go. There we go. All right. So let's check out what we have talked about already. So I'm just going to quickly go over these topics. So we did talk about section 3, and let me kind of zoom in a little bit so it's easy to read. So we talked about what is alpha. Alpha is basically each element of alpha is a symbol. Every element of omega is an operator. And between alpha and omega, we can actually create or define the well-formed formulae. So basically, you just have to play by the rules. If a particular omega operator requires two operands, you supply two operands. And if it requires one operand, you supply one operand. And once you have an expression that is well formed, that in return can be used as a component for another operator. So it's a recursive definition of what is well formed when we combine alpha and omega. Oh, the other thing that is really important is everything in alpha by itself is well formed. And then so you basically build on top of that. Zeta, on the other hand, is a set of transformation rules, or we can also call those productions or inference rules and so on. But each inference rule is basically a syntactical transformation of some patterns that we recognize. And last time we talked about that, just a little bit. And then iota would be the set of well-formed formulae that are known to be true to begin with. In other words, those are the axioms. We don't question why those particular well-formed formulae are known to be true. So those are the 5 components that you need in order for a propositional logic system to work. So you can dig up, the propositional logic system, and there are some really kind of interesting rules. I will show you some interesting rules here. And since I cannot get my tablet to hook up to my network, so what I can do right now is to actually I just thought of a way to potentially be able to do it, because the tablet is potentially capable of using a USB cable and can network through the USB to my laptop computer. Unfortunately, I don't have an extra USB-C cable right now, so I can't really quite do that. Um, hmm. Yeah, let's not mess around with the network, because I can explain the same thing without using the tablet. I'm just going to be using. Ooh, wait. Okay, this is even better. The reason why I got this particular laptop computer is because it has its own digitizer. It is a tablet itself. I almost forgot about that. Really cool part. All right, so I am going to start up another program called Zernal, and we can do Zernal PP, Zernal plus plus. There we go. Let's see, that starts up okay. So we can put it here where it is viewable to you. Excellent. All right, cool. And we'll go ahead and nope, it doesn't let me do that. Okay, that's fine. I'm gonna pull out my pen, and now I can start to write on this screen. And I'm just gonna check on OBS to make sure that it is capturing the entire notebook here. There we go. So I'm just maximizing the area, so this way you can, I can write a little bit more before I have to scroll. That's all. All right. So now we're gonna take a look at some transformation rules. So a transformation rule has 2 sides. Okay, one side is a set, and then we have the inverse. Okay, this symbol here, the inverted, not inverted, but rotated T means inverse. And then on the other side here, we have another pattern. So this, what we specify here, is a set of pattern. So let me just kind of right here. This is a set of patterns. And then on the other side is a single pattern. So the idea for this to work is we are going to define a set of patterns so that when all of those patterns, are matched, then we say, we got a match. And then once we have a match, then we borrow, the components in the set of patterns to create this new pattern here. And each so-called pattern by itself is actually a well-formed formula. Okay, so last time we took a look at some not so interesting ones. Okay, and then we took a look at one interesting one. So let's go back to what we talked about last time. So last time I think the first one that we talked about is something like this. It starts with let's start with phi in this case. Let's see, phi is this. This is phi, and then this is psi. Okay, because we usually use at least 3 Greek symbols in alpha, and these are called schemata instead of a variable. And then we basically say this infers phi and psi. Okay, so that's the inference rule. On one side, we have a set of patterns, and then on the other side, we have a new pattern, which basically says if I try to match all the well-formed formulae that are already known to be true, one is just phi by itself, which basically says, yeah, I can match any well-formed formulae that is actually true at this point, and the other one is just psi by itself, which also doesn't is not very restrictive as a pattern because it just says, hey, I can match any well-formed formula too. So this is just going to bind to some well-formed formula that is known to be true. This is going to be binding to a well-formed formula that is known to be true, and they can bind even to the same one. Okay, there's no restriction of they cannot bind to the same one that is true. So once this side is possible, once I make binding that makes the left-hand side work, then the inference is basically saying, okay, now I can create a new well-formed formula, and that is also going to be known to be true. Okay, so I think last time we also used an example, right? And I can actually get back to the notes from the uh, um, desktop application here. So let me get back to the notes from last time just so that you guys know what I am talking about. There we go. All right, so this is what I'm talking about from last time. So if you kind of still remember what we talked about last time, this is what we talked about. And I'm gonna hide this one again because I just want to make a reference to something that we talked about previously. And then what we'll do today is to look at some other inference rule. The reason why this one works, okay, this particular one works, is because we know that individually phi is true because otherwise it would not bind to the left-hand side of an inference rule. We also know that psi is individually true because otherwise, guess what? It's not going to bind to the psi symbol because it's not a well-formed formula that is known to be true. So by themselves, phi and psi are representing each one is representing a well-formed formula that is known to be true. So now that you have two well-formed formulae that are known to be true, but they can be the same one too, it's easy to conclude that the conjunction between those two would also need to be true. So this is fairly standard, okay? There are some other ones that are really kind of useful. One is making use of implication. So if you know that phi on its own is true, and then you also know that phi implies psi is true, okay? So this time it's a little bit more restrictive. Psi itself can bind to any well-formed formulae that is known to be true. Not a problem. But the second item in this particular set is a little bit more restrictive because whatever psi is bound to, that psi has to be exactly the same psi appearing as the left-hand side of an implication. The right-hand side of the implication is psi, and there's no restriction of what psi can be. So that means the second thing that I list here in the set has to be in the form of phi being on the left hand side implies and then some other expression that is psi on the other side. But on the other hand, if I can find something like this, then I can infer the following because I can now infer psi all by itself has to be true. Okay, so that's one really useful inference rule is just using the implication because once you know the left hand side of the implication is true, then the right hand side is also guaranteed to be true. So now we're going to move on to something that is a little bit awkward. Okay, so to realize how awkward these things are, let's actually just go ahead and define alpha. So alpha typically has 0, which is what I use for false, 1, which is what I use for true, and then we have some variables, which is P, Q, R, S, T, to have 5 variables, and then we have the Greek letters. Typically, we only need like about 3. Phi is 1, psi is 1, and then, oh, I used that one already. Let me undo. There we go. So we're gonna have phi, psi, and theta. Okay. So this is the typical, alpha that most your textbooks would choose to use. All right. So Jonathan says, how do we differentiate between your 0 and phi? I would say it's the length of the stroke going through and the size of the circle. But that's a good point. I I can see where the concern's coming from. Yep. Um. All right. Okay. So getting back to this one here. So now we're going to start a rule that says, hey, it's an empty set. In other words, I don't even need to look for any particular pattern because I can always say that whatever this side is, I can always say give me any variable, and we can say that P or not P has to be true, right? Because between P and not P, one of those two has to be true, one of those two has to be false. So that means I don't need to know anything ahead of time. I can already make this conclusion here. Now, in reality, we don't want to use P, so we're gonna use, oh, this eraser is too big in size. Let me see what I can do here. Hmm. All right, so let me do the next best thing, which is this. So we're going to use an empty set on one side in first, and then you can just put, phi or not phi on this side. So this phi can bind to anything. It doesn't even have to be something that is known to be true. It just has to be a well-formed formula. Are we still doing okay so far with the discussion of the inference rules? Why each one seems to make sense. Okay, very good. So, given that we have all of these inference rules, what are we doing with these inference rules? That was something that we talked about last time. Because remember last time, okay, that first thing in the set is a 0 and the last is a theta. That is correct. So this is a 0, this is phi, and this is theta. Yep. All right, so let me remind you, how we are using these inference rules. So let's just use this as the line, the kind of defining, the well-formed formula space. So we'll say, oops, okay. So we'll say this is the well-formed formula space, which basically means it is a set containing all the possible well-formed formulae. And last time we already talked about this, and we conclude that this space is infinitely large because there are a lot of stupid, expressions, even though they are quote unquote stupid from the perspective of why would we even look into those well-formed formulae, but they are nonetheless well-formed. So the space itself is going to be infinitely large. So within that space, and let me switch to a different color, which is red. So we have things from iota, which are the ones initially red to begin with. And it's going to be finite. It's going to be very few of those that are known to be true. That is, they're basically axiomatic. And then what we do is we try to use these production rules so that we say, okay, I'm going to change the color again. So now we can say, hey, if these two are true, then we know this one is true too. Okay, so we just basically use this to represent an inference, the application of an inference. Okay, so the application of inference is not really producing a new well-formed formula per se. It is basically just labeling another well-formed formula and say that, hey, since we know this one is true and this one is true, and they match something along this line, now we know this one, which is corresponding to this pattern here, is also true. So we basically keep applying these inference rules, and the objective is to say, see this little green dot over here? We want to somehow label that one to be true too. Or we are asking the question, can we eventually label this green one all the way here to be true by repeatedly applying these inference rules that we have talked about here, starting with the red circles, which are the things inside iota, and then keep applying these until we can reach here and label the green circle to be true. That is theorem proving. This is the proposed theorem. The green circle is our proposed theorem. And what we want to do is to be able to label the proposed theorem to be true because the red ones are labeled true to begin with. That is theorem proving. So I'm gonna let you guys think about this a little bit when I'm gonna go mess around with my touch screen settings, because I need to turn off the touch screen so that when I rest my palm on the screen, it doesn't automatically trigger the Windows. It doesn't activate the other window when I don't want it to activate. So you go ahead and think about this a little bit and see if you have any questions to ask. And you can see what I'm doing here, and I'm just turning off the finger touch aspect. We want the pen to stay. Yep. Okay, so all of these can stay except for the one that I just turned off. All right, cool. All right, so I'm back. All right, Jonathan has a question. All right, so Jonathan has a question, and the question is, when proving something, do we need to outline true statements that aren't important to the proof? I'm gonna, I don't even want to answer the question because guess what? We are not gonna do this, okay? If you take this class from most other professors, they're gonna ask you to practice, proving theorems using, all of these, inference rules, and there's a big, huge set of these inference rules, okay? But in this class, we're gonna do it in a slightly different way, okay? But let me think about the question a little bit. When proving something, do we need to outline true statements? I'm taking that as well-formed formulae known to be true that aren't important to the proof. So that really is the difficulty of proving a theorem, because for those of you who have taken algebra or taken any class that requires you to prove theorems, you can do a whole bunch of derivations, and sometimes you're just going in a direction that is not helpful. And that's basically what Jonathan is asking is, are those other steps important, because they don't seem to help me to get to the green circle over here. The answer is you don't really know until you get to the end, right? Until you get to the end, then you can probably find out what is the minimum connection between the dots that can get you to the green dot over here. But before you get there, you cannot really quite say whether some of these dots over here is not along the path to get to the green dot or not. Does that kind of answer your question, Jonathan? Okay, cool. All right, so let me explain to you why this is a problematic approach to do things. It mostly has to do with this space over here is infinitely large. So you can think of this as a haystack that is infinitely large. And what you're trying to do is to find a needle in a haystack. Okay? So when people say, oh, you're asking me to find a needle in the haystack, this is a slightly modified problem, okay? Because sometimes we don't even know whether the needle is in the haystack or not. Now, obviously, the well-formed formula is already in the space, but we don't know whether it is actually a theorem of what is given to be true to begin with. So, in the analogy of a needle in a haystack, it basically means, I'm trying to ask you to find a needle in an infinitely large haystack, and sometimes the needle doesn't even exist. So, how can you confirm that the needle does not exist when the haystack is infinitely large? Now, if the haystack is finite, okay, if the haystack is just big, it's just going to be a whole lot of chore to go through it to find the needle. But if the haystack is finite, that means eventually you can look everywhere and then you can come back with a conclusion and say, Tack, you just tricked me. The needle is not even a haystack. And I'll just chuckle and go like, yeah, well, I was just testing you. Right? Which is kind of nasty for me to do, but it is not impossible for you to answer the question. On the other hand, if I give you a haystack that is infinitely large, and I say, find that needle in this infinitely large haystack, then there's no way for you to differentiate between the needle is not actually in the haystack or that you have not found it yet. Okay, so that is a kind of a nasty problem to deal with. So what we're going to do is we are going to introduce a few new concepts so that we can basically prove theorems without having to worry about, oh, we have an infinitely large haystack. Nope, we are going to make the haystack finite so that even if the needle is not in a haystack, we can come back with a conclusion within a reasonable amount of time and say, that needle is not in a haystack. I know because the haystack is only finite and I have searched everywhere already. We can make a conclusion really soon. So that's what we want to do. Now, in order to do that, I'm just putting my stylus back into its own little charging port on my computer. So what we want to do is, okay, let me go back to my notes here. Oh, there are a few concepts that we have to talk about, which is completeness and soundness. So it's kind of important to talk about these two. Um, at the end of the day, completeness simply means everything that we can do by hand, the mechanical system using propositional calculus should be able to do it too. In other words, we just want to make sure that the mechanical system is not implementing only a part of what we know about Boolean logic. Soundness, on the other hand, means if the mechanical system can prove something and proves it to be true, then we should be able to do it by hand too. Okay, so one has to do with correctness. Soundness is kind of related to correctness, and then completeness is about is the system competent? Is it as competent as we doing it by hand? So obviously we want a logic system that is both complete and also sound, and the rest is really just a kind of symbolic way to define and to explain the same concepts. So that's what section 4.1 is about. All right, so now we are moving on to section 5, which talks about resolution. So resolution, as an English word, obviously has certain meanings, but in this context, in the context of propositional logic, resolution has a very specific meaning. So in order to get to that very specific meaning, we're going to go through this derivation here. Now, yes, in this class we do have to understand Boolean expression, Boolean algebra, because we are going to have to transform certain kind of expressions into another format. That is why we need to understand Boolean algebra, and there will be some additional stuff in this module that talks about Boolean algebra. So we start with something like this. We have phi or psi as a whole thing, and not psi or rho implies in this case there's an outer parenthesis around these two because the priority of conjunction is higher than the priority of implication. So I'm claiming that this particular conjunction implies phi or rho. Okay, so I want to see what we can go with this in terms of using Boolean algebra. So the answer is let's try to apply those things step by step. The first thing I do is to transform the implication into the negation of the left-hand side of the implication, or the non-negative version of the right-hand side. And therefore, we see the negation symbol here. The negated part would be the entire left-hand side of the implication. And then we have a regular or, and then we have the right-hand side, which is just this part here. Is that okay? I hope this reminds people of how implication can be defined using A implies B really is the same thing as not A or B. All right, cool. And then from the first line to the second line, I use De Morgan's law. So De Morgan's law, you can sort of look at it as the distribution of negation. So we are distributing the outer negation into the components inside, in this case, a conjunction. But in doing so, I also have to change the conjunction into a disjunction. So that is the application of De Morgan's law, taking it from the first line to the second line. And I also did some syntactical change, because when everything are connected by ors, then we don't really need the extra parentheses anymore, because or is commutative, it's also associative. So we don't really care about the ordering of which one is ORed with which one first, and so on and so forth. And then from here to here, we are applying De Morgan's law again. So in fact, we applied De Morgan's law twice, once to this particular OR, once to this particular OR over here. Now, it is important to understand that this OR expression is itself negated first before it is ORed with other things in this particular expression. So that's why this particular OR cannot be commutative with this OR over here. But since this is a negation of an OR, we can apply De Morgan's law. So once again, De Morgan's law is sort of like the distribution of negation. So I'm applying the negation to the components of the OR, but by doing this, I also have to flip the OR operator into an AND operator. I do the same thing over here. Okay, so we have the components here that are being negated. So I distribute the negation, and in this case I combine the double negation and cancel itself, because not is basically just going to cancel itself out, and then the not row needs to stay with the negation. But every time I apply De Morgan's law, or becomes and, or in some cases and becomes or. So basically you have to flip the operator when you apply De Morgan's law. And then from here to here, from the third row to the fourth row, I do something that doesn't seem to be making any sense, because I say basically, oh, here is phi, and I'm changing phi to phi and true. Here's row, and I'm changing row and true, because anything and true is just whatever you start off with, because that's an identity. Let me ask you this question, okay? I'm directing this question to the whole class. How can you confirm that true is in fact the identity of conjunction? In other words, how do you know for sure that the phi by itself is really the same thing as phi and true? What would be the technique that you use to prove that to yourself? It's one of the techniques that I talked about from the really early part of this class. And we got 2 people typing. All right. And Jonathan is correct. A truth table would work. So I'm going to show you the truth table right now, because I think it is very important to understand how useful truth tables are in this context. All right, so I'm going to get back to here, and now that it has palm rejection, I don't have to worry about resting my palm on the screen because it's kind of difficult not to do that. Um, but it also means I cannot use my finger to scroll, so I have to use the pen to scroll in this case. All right, so we only got one independent variable. Oh, this is an awful color for doing normal stuff. So we only got one independent variable, which is psi. This is phi, by the way. I just mispronounced. So phi itself can be false. It can also be true. Okay? And now we look at the expression that we claim is really the same thing as phi by itself. That expression turns out to be phi and true. So now you have to fill in these two cells and you ask, okay, if phi is false, what is false and true? Okay, that is just false. If phi is true, what is true and true? That is just true. So now we have just established that regardless of the value of the independent variable, the expression is always the same as the independent variable itself. And this is a very quick way to prove that true is the identity of the operator known as conjunction or AND. So there we go. So truth tables are very, very helpful when you want to just prove to yourself, why is this expression the same as that expression? All right, so getting from the fourth row to the fifth row, what am I doing here? Well, guess what? I'm making things even more complicated now. Because instead of a true here, I say, instead of writing true, I'm just going to write this out as psi or not psi. Now, psi or not psi has to be true because of what I just talked about earlier. Because between psi and the negation of psi, one of them has to be true, the other one has to be false. But because we are joining those two with an or, that means the entire or has to be true. Some of you may not be convinced at this point and go like, can you prove that, Tack? And some of you are already thinking, yeah, we know how Tack is going to prove this one. It's going to be using the truth table again. All right, so why not? So this time I use psi as an independent variable. It can be false, it can be true. And now we look at psi or not psi. Okay, so when psi is false, not psi is going to be true. And since we have at least one side of the or being true, the entire thing is going to be true. When psi itself is true, psi or not psi is going to be true because psi itself is true. And this time it's the left-hand side that is true, but since we only need at least one side to be true, so the whole thing is going to be true again. So obviously this doesn't really show that psi or not psi is true, so we are just going to have one more column for the constant expression here, which remains true regardless of the value of psi. So now we look at this column, and then we look at this column here, and we say, hey, they look the same for every value of psi, so that means these two expressions are equivalent to each other. So that's another way to use a truth table to kind of show to yourself, why a particular expression, a Boolean expression, is equivalent to another Boolean expression. And I think just thinking in this way is helpful because it basically it helps you understand how we can transform Boolean expressions using these Boolean algebra rules. All right, so now we got the true to psi or not psi. We got this one also to be psi or not psi. From the fifth row to the sixth row, we use distribution. So as it turns out, distribution works in both ways in Boolean algebra. So I'll explain what I mean by that. But in this case, phi and psi or not psi is expanded or distributed to psi, phi and not psi, or phi and psi. Okay, so what exactly is distribution and what does it look like in Boolean algebra? So I'm going to switch to this screen here. So it works in two ways. So if you have A and B or C, you can distribute it as A and B or A and C. Okay, so from this perspective, you might say, oh, so and is kind of like multiplication, and then or is kind of like addition. Well, I'm not going to get into abstract algebra, but those two, these two pairs of operators actually do have similarities in abstract algebra. But we're not going to get into abstract algebra in this class. But the next one is less obvious because we don't have the equivalence in arithmetics. So if you have A or B and C, then we can actually say that this is equivalent to A or B, the whole thing, and A or C. So distribution works in both ways in Boolean algebra, but obviously only works in one way in normal arithmetics. So if somebody is asking, how can we prove that this expression is really the same thing as this expression here? Because in my mind, it doesn't work out. Well, my recommendation, I think some of you already know the answer to that particular question. So get out of your mind and put it on a piece of paper and use a truth table to prove it. Now, it's going to be a longer truth table because we have three independent variables. We got A, B, and C as independent variables, which basically means you end up with 8 rows because when A is false, B can also be false or true, and then when B is also false, C can be false or true, so you will end up with 8 rows. But I can guarantee you, of all 8 rows, whatever this expression turns out to be, it's also going to be what this expression is going to turn out to be, and that's why we have this particular rule that allows us to do the transformation. It goes the other way too, so when you see something like this, you can go back to this form by factoring, and also when you see something like this, you can go back to this form using factoring. Okay, so that's how algebra works out in Boolean operations. Alright, so getting back to this proof here, so we just use distribution so that this sub-expression becomes these two, this sub-expression becomes these two, and then what do I do next? Let's check it out. So next I do factoring, okay? Because I can see that we have not phi and not psi, and then we also have phi and not psi over here. So we do factoring so that we basically we end up with not phi or phi, the whole thing, and not psi over here. We do another factoring because we have psi or rho, and then we have psi or not rho, on the in the line above. So one is over here. This is psi and not rho, and then psi and rho is all the way back here. So we use factoring to come up with this term over here. Oh, well, it's basically the application of those rules that is important. And since I have proven this already here, you're not going to prove the same thing, although you're going to have your own exercise of using Boolean algebra later on. Alright, so now what do we do? Well, we are just reversing the process now, right? Because we can see that this is not phi or phi, which turns into a 1, into true. And we look at this one here, which is rho or not rho, that turns into true too because of this simplification. This is simplification. It's the reverse of what we just did earlier. And then the other two, we are not doing anything with those just yet. So now we end up with psi all by itself, which is a simplification because and one and whatever is just whatever, and then whatever and one is also just whatever. So psi becomes all on its own. And then we say, hey, now we see not psi or psi, right next to each other, and they're in the same OR. Okay, which means as far as this entire OR operation is concerned, it has to be true. There's no way it can be false. All right. Yes, I know it's kind of, you might need some extra time to go back and watch this again and clearly identify what I did with each row, And that's something that you can do with Zerno. Just print the PDF, print the HTML as a PDF, and then the program that I'm using, which is Zerno++, would allow you to kind of put in your own annotation um, into the document. I mean, you guys have fancy programs and fancy tablets and fancy iPads to do all of this good stuff here. Or for those of you who prefer to be tactile, you can do it on a piece of paper. Just print it out and then use your ink pen and just to or pencil to comment and annotate it. Okay, but what does that mean? What does this mean? I mean, looking at this entire proof here, what is that telling me? I mean, you start off with some kind of random Boolean expression, and we end up with just true. What does that mean? Well, it means one thing. Okay, it means regardless of what phi, psi, and rho used to be, this implication is always true. And the only time when you can say an implication is always true is, oh, if the left hand side is false, then the whole implication is true. But that is not very helpful in our case, because in a propositional logic system, we only want to pay attention to well-formed formulae that are known to be true. So we are basically saying, let's pick something like this to be true. Let's pick something like this to be true. But this is allowing us to create an inference rule out of these two that ends up with this OR expression here. And some people look at this and go like, so what is the big deal? I mean, there are many other things that we can say, regardless how you choose these three, Greek letters, it's going to be true too. So what is so special about this one? What is special about this one is in the process of the application of this inference, we are removing a component because we start off with this, okay? But what we end up with has one of the Greek letters gone because we start off with three Greek letters on the left-hand side. We need phi, we need psi, and we also need rho. But what we end up with is an expression that doesn't have psi in it. It only has phi and rho in it. This is why it is really nice, because eventually, by repeated application of this particular resolution logic, we can end up with nothing, right? Which is, by the way, the secret ingredient of the soup that Goose makes in Kung Fu Panda. The secret ingredient is nothing. So in this particular context, the secret ingredient is also nothing, because if we somehow use this kind of transformation and we end up with nothing, that's actually a very useful thing, okay? But I am a little bit ahead of myself, because until we understand what is proof by contradiction, that connection is not going to be clear. So now we move on, okay? So what we do is now we end up with this inference rule to basically reflect what we know is semantically true, okay? So what we know semantically true is this implication, and what we are now doing is we are now turning it into a mechanical pattern matching thing to basically say, hey, look at all the well-formed formulae. If you can find me something that is an OR with phi and psi, bound to certain components of that disjunction, and if you can find me another disjunction that has not psi. Now, this not psi, the psi in the not psi, has to be the same thing as this psi over here. So we are now putting a pretty we are restricting what two well-formed formulae we can use in order for this particular inference to fire, in order for it to be applicable. So if you can find me something that looks like this and something that looks like this, where one of the components is non-negated on one side and it is negated on the other side, then we can apply the transformation rule, which is a mechanical process, and we end up with a well-formed formula that looks like this, which is only phi or rho. Psi is basically gone. Okay, so basically, if you can find something like these two that are labeled, that are known to be true, then we can label this guy also to be quote unquote known to be true. So does everybody understand the connection between this crazy derivation here, which end up just saying that, oh, this implication is always true, and the inference rule that is based on the theorem that we just proved? Are we seeing the connection? I know it is kind of obscure, but just looking at the big picture, okay, we are now basically saying, okay, since in terms of Boolean algebra, we can show that this always works. Now we just say, we'll just go ahead and transform that into a mechanical thing so that the computer can do it. So the computer is just doing a pattern matching and say, if I can find this pattern known to be true, if I can also find this pattern known to be true, then I can label this new pattern also known to be true. But the nice thing is the new pattern has one fewer component compared to the two things, the two well-formed formulae that we have chosen to use from the beginning. Then you guys would go like, oh, great, we just end up with another inference rule in all of those inference rules that, we people actually use when we are applying, Boolean algebra. Well, this is also the other thing that is really cool is by transforming things, by doing certain other things, this becomes the only inference rule that we'll ever need to use. In other words, forget about those crazy inference rules that we talked about earlier. Let me go back to some of those crazy inference rules that we talked about earlier. Let me. Okay, so this is from the previous class, and let me see if I can. Yeah, we can do that. And I think, oh, okay, maybe not. Because I'm trying to look for the application of an inference rule. I did not specify here. But we certainly did it today. So I'm going to look at the notes that I took today and scroll up a little bit. So instead of having these inference rules, over here, and then we got this one, and we got this one, and there's a whole bunch more, okay? When you look at the inference rules that reflect how we as people work on propositional logic, there's a whole bunch, okay? Which is also contributing to why it is difficult to prove a theorem, because which one do you choose to apply? If you have four of like 16 rules that are applicable, which one are you going to apply? I mean, that makes proving theorems difficult. So what we're going to do instead is we're going to change the rule of what is considered a well-formed formula. So these are the new rules. Okay, so this whole system is under new management at this point. So the new management says, okay, we have only one element in omega 1. In other words, there's only one operator that requires one single operand. And it's, guess what? It's just negation. Okay, well, that's kind of the same as before. But we also only put one single element into omega 2. In other words, of all the operators that we know that requires two operands as Boolean operators, we're only keeping or. We toss, we don't need and, we don't need implies, we don't need if and only if. We're only keeping or. That is kind of odd. And we also changed the rule of what is well formed. So instead of talking about what is well formed right away, we're going to say, is ADE, which is the abbreviation of is a disjunctive element. Okay, so what is a disjunctive element? Well, a disjunctive element is everything in alpha is automatically a disjunctive element. Okay, so that means 0 by itself is a disjunctive element, 1 by itself is a disjunctive element, and then all the English, all the letters that we borrow from the English alphabet, P, Q, R, S, T, each one is also a disjunctive element. All right, so that doesn't sound too bad. And we are also extending the definition of what is a disjunctive element to the negation of any element of alpha. So that means the negation of 0 is a disjunctive element. The negation of P is a disjunctive element. The negation of true is a disjunctive element, and so on. Okay? So basically, if you just choose anything from alpha, whether it is negated or not negated by itself, it would still be a disjunctive element. Where are we going with these disjunctive elements? So the next one makes use of disjunctive elements. So in this particular um, definition, I am supplying you with a bunch of phi i's. Okay, so there are n of these things because I is an index. It goes from 1 to n. So I'm giving you n phi's. Okay, so I'm giving you n disjunctive elements because is ADE confirms that each phi I is a disjunctive element. Now we get to is a well-formed formula. The OR of all of these disjunctive elements is well-formed. And that's it. Those are the rules. Okay? So let's check out, using a few examples of, what is considered well-formed when we are under this new management. And I think this is going to be all the time that we have, for today. You have a 5-day weekend, so that means over the long weekend you should try to complete this entire module. Try to read through the entire module. Certainly go through the things that we have already talked about and make sure that you fully understand those particular concepts. But on next Monday, we're going to talk about CNF, conjunctive normal form, and how we can turn everything into conjunctive normal form. There is an actual example in here, right here. This is an example. It may not be the best or the quickest way to do it, but it is one way to do it. So I would like you to at least get to the example here and understand how we start from here and end up with here. We are not taking row today because I just simply did not have enough time to set up everything because I got my training done shortly after 4 o'clock, and then I had to run outside and refill the generator with fuel and then run back inside, set up this environment, set up my cell phone in order to teach this class. So I didn't have time to set up the road taking thing. So for people who have been waiting to do the road taking thing and then so that they could take off right after the road taking thing, I sincerely apologize. Anyway, getting back to this. Alright, so let's check out the new management system and find out what is well formed. So once again, alpha is going to be false, true, P, Q, R, S, T, phi, psi, and rho. So no theta this time, just rho. Okay, so what is well formed? This is well formed. This is well formed. This is well formed. This is well formed. Nope, I take it back. Sorry, nope, not well formed. These are disjunctive terms. Okay, these are disjunctive terms. What is well formed is if you just take any number of the disjunctive terms and turn it into an OR expression, that OR expression is well formed. So 0 or 1 is well formed. P or not Q is well formed. Not P or Q or R is well formed. 1 or this is 1 or P or Q is well formed. So all of these are well formed under this new set of rules. And then the next question is, what is not well formed? Okay, because it looks like there's a whole bunch of stuff that is well formed. So what is not well formed? So let's take a look at those things. And first of all, I need to make a new page. So not sure how I can. Oh, there we go. And did I give him a new page? Nope. New layer, new page. There we go. Okay, so here's a new page. So it is important for me, I know we are going a little bit over time, but it's important to understand what is not well formed. Not well formed. Okay, so not P or Q. Okay, that is well formed, but if you negate the entire thing, it is not well formed. So this is not well formed. If you say P or Q, um, yeah, so the only time you have something that is not well formed is when you put a negation to something that is not something from alpha. Otherwise, it's pretty hard to break that rule because you only got one operator that can take two operands. So the only restriction is when you use negation, you can only negate something directly from alpha. But you can OR a whole bunch of things together. Okay, as long as whatever you're ORing is a disjunctive term, a disjunctive element, you'll be fine. All right, so we are out of time today. I am going, there's no homework at this point because I cannot give you a homework, because the next homework is going to be transforming a normal Boolean expression into what we call CNF, which also means this is also why it's important for you guys to preview what is CNF, because once you preview what is CNF, it will make the next lecture a whole lot easier to understand. All right, so you guys have a nice weekend, and I will work on my key generator program to generate an HTML as your key, and then I will share your answer to the exam and also the key with you, so that way you can basically go through all of your own answers and compare your answers to the key and see whether you got it right or not. All right, so Jonathan is typing. Yep, you guys have a nice weekend too. And for those of you who are really concerned about your grade in this class, you might want to go back to the syllabus because the boundary between the letter grades are different in my classes compared to a quote unquote normal class. Um, it does not imply that people cannot fail in my classes. Okay, I have to tell you that since COVID, my assembly language programming class, has more people failing that class than before COVID. But that's a different story for another day. But I do want you to keep in mind that the percentage boundaries are different in this class. So you guys have a nice weekend. I will distribute your test and the key to you hopefully sometime tonight, but I still do not have power back. I'm actually running on my um, solar battery, from camping, from going on camping trips, and it's doing a pretty good job. I mean, looks like everything continues to work here despite I'm using a completely mobile setup at this point. Anyway, have a nice weekend. I'll see you guys next Monday. Bye.